Yeah, thank you very much, Miguel, for invitation and for the introduction. So welcome everybody. Today we are going to be talking about this beautiful paper. My name is Anton Trunov, and this is Jesus Dominguez. He will be presenting this hardcore stuff about category theory. So we work at MDA Software Institute. It's near Bodie del Monte and Pozuelo del Arcon. I'm a research programmer there, so if you want to get in touch with me, you can address me on Stack Overflow, Twitter, or like on GitHub. I'm kind of active in this COC tag on Stack Overflow. And Jesus Dominguez is a PhD student at the same institute. His main research interests are logic, type theory, concurrency, stuff like that. So a little bit about our backgrounds. I switch between industry and research institutes. Like I worked several years there, and I did C for embedded microprocessors. I did some stuff for supercomputers like MPI, CUDA, OpenMP, stuff like that. And Jesus worked as a Java programmer as well before joining the going into research. So let's dive into the paper, right? Why do we love it? It's very simple. If you are familiar with functional programming, by the way, who can say that you're familiar with functional programming? Okay, all right, so that's very good. This paper starts with the basics, so I hope it won't be too boring for you when we will go over these basics, because we didn't really know your backgrounds, right? And also, it teaches you how to calculate your functional implementations. Calculate. So there is a systematic way of producing functions. Of course, it's not really calculation in a sense, like you have an arithmetic expression and you know how to reduce it basically to one number, right? But it's a very systematic approach of like mechanized derivation. And we will see how it works. And also this paper provides a very good overview of the area, which consists of recursion schemes and stuff like that. So it generalizes over arbitrary data types, basically. So we start really simple, right? This is the sum function, which takes as its input a list of integers and produces their sum, right? Very easy. You all know what to do here, so we pattern match on the list in case if the list is empty. So we don't really have anything to do but return 0, right? It makes sense for sums, right? Okay, if we have non-empty list, we just add its head to the rest of, we just recurse basically, right? So we sum the rest of it. It's basic recursive function. Okay, let's have this thing. We have a list of booleans, right? We want to see if all these booleans are true, right? And the implementation of this function follows exactly the same pattern, right? As you can see, you have the head of the list, and you have some operation, and you have the rest of it, right? So does this make sense? Okay. So let's take length. It takes a list, and it computes its length, right? For empty list, it's 0, of course. Then we don't care about the head of the list, which this underscore says. By the way, this is Haskell, right? So I hope you can read Haskell. It's pretty readable, right? Like mathematics. All right, and we compute the length of its tail of the input list, and we just increment it by 1, right? Super easy. Map is easy as the rest of them, right? You just take an element, you map some function over it, and you const it with the rest of map, right? Of map over the length of the list. All these implementations follow this simple pattern. You have some you have some list of type A, and you want to reduce it to some value of type B. So in case of empty list, you need to supply some value V, and in case of const, so if you have a non-empty list, can you see the point? I cannot either. Okay. All right. Sorry. All right. So in this case, you just take some combining functions or operator, and you combine x with the result of recursive call of rec over the tail of the list, right? More of these patterns. For example, the reverse function. By the way, I'm not saying that what I'm showing is like the most efficient implementations, right, of these functions. It's just a way of constructing those functions systematically. This is what we're pursuing here. So in the talk, we will assume that all the lists, they are finite. We won't be discussing laziness, for example. So we're like working with pseudo-Haskell, let's say. Okay, so how do we implement reverse? We can reverse, well, I won't cover the obvious case, right? We can reverse the tail of the list, and then we should slap the first element to the end of it, right? Which is the snock function does. Snock is const in reverse, right? All right, so filter. Filter has the same pattern, right? You have so-called conditional const. Conditional const does what? It takes some predicate p. It checks if this new element x satisfies this predicate. Then it slaps it with some tail. Otherwise, it throws it away, forgets about the element, right? This is what conditional const does. And so filter, this classical functional programming function, can be implemented in the same form, right? Here we have this append function, which concatenates two lists, right? It has sort of the same pattern, but we will see it's not exactly the same. But basically, we can implement. This is a legit implementation of const. Sorry, not const, append, and we will see how we can derive it a bit later. So how do we implement this rec? Well, thanks to higher order functions, we can pass functions as parameters, right, in functional programming. We can sorry. So in case of empty list, we just return this v value, some value of type b. In case of non-empty list, we use some function f, the folding function, to basically combine new head of the input list with the rest of our computation. Yeah, we just recurse. It doesn't work, sorry. Okay. So, are there any questions at this point? I guess this is tutorial, right, for you guys? Or no? Yeah, feel free to ask, to interrupt me at any time you want. Like, let's make it more interactive. Okay, thank you. Yeah, okay, that's cool. Thank you very much. It's sort of an arbitrary function. It has to have this type, right? So it has to take this element of the list. So we have a list of type A, and we have this accumulator type, right? So it takes an element of this list, the input list. It takes the rest of this accumulated value so far, and it produces new accumulated value. So how does it work? Let me go into this graphical representation, sort of. So folder, this is F, right? I use this screw symbol for the reasons that will be clear later. Okay. So we have some list of length n. Here I just listed all its elements. And so fold right basically starts with the from the end of the list, right? So it takes xn, it combines it with v, and then the result combines with xn minus 1, combines with, and so on and so on and so forth, and until it combines it with the first element of the list, right? So compared with this representation, this is just, this form is a desugared representation of list, right? So this is a sugar, syntactic sugar, which Haskell gives us. But actually, lists are represented this way, right? So it's the end of the list, this end marker, and then we slap more elements on top of it, right? So what folder does, it replaces this new element with v. It leaves xn minus 1 in place, and it replaces the cons operator, the cons constructor, sorry, with this screw function, with combining function. Okay. So this is what I just said. If we look at those functions that we use as motivational examples, we can see that sum actually sums all the elements of the list from right end until the beginning, right? It uses 0 as its accumulator, starting accumulator, right? All can be also implemented using fold right. Fold right, actually the name comes from this order of the parentheses, right? In mathematics, they say they associate to the right. All right. Then length. Length is basically we replace the nil constructor with 0, and the rest of the elements, we replace with +1, right? Basically, which is this point-free style function says, right? Point-free style const means that we take the incrementer, which will forget the next argument. Why do we need to forget it? Because we need to ignore the elements of the list. We are concerned only with the form of the list, not with the exact elements. Right, map. Map can be written as fold right as well. So you replace empty list with empty list. You replace every element with f of it. We basically map, right? And we just slap it again on top of the accumulator. So our accumulator will be a list, okay? Reverse. Reverse has the same form, right? So we just say folders knock of empty list. So if we go through this computationally, so we take empty list, we put xn at the end of it, then we put xn minus 1 at the end of the accumulated value, and so on and so forth, and we put x1 at the end of our list being accumulated, right? So filter is the same thing. So we use this pattern. We just basically take these combining functions. We take the initial value of the accumulator. We get what we wanted. But append, on the other hand, is not exactly the same. It doesn't have exactly the same pattern. So if you look at it in point-free style, so we need to flip folder. This is because append is a binary function. It's not commutative. And commutative means you can swap the arguments, right? So, but it works using the same pattern as we used before. So you take x, the input list, xs, sorry. We replace its nil with ys, and then we basically repeat its construction again, right? And in the end, we get concatenated list. All right, so advantages of using fold. It's can be less boilerplate, right? Can be easier to understand once you know how this pattern works. So this code is constructed in a systematic manner. It allows for easier code transformations, like by the compiler, for example. Also, it makes it easier to reason about it, and we will see this reasoning part closer to the end of the talk. Right, but fold, as you might have guessed, is not a silver bullet, right? As everything in programming. Let's take this classical function, drop while, which works like so. It takes some predicate p, some Boolean predicate, and it drops everything that satisfies this predicate, but only until we have something that does not satisfy it. So it basically drops this prefix, the even numbers. Notice that it doesn't drop all the even numbers, right? It's not like anti-filter or filtering out. So this function actually does not follow that pattern that we saw before. And why? So you see, we have this recursive invocation, right, of the function, which fits that pattern. But when we go through the list, here we're saying, okay, this element, let's say this, the first one, satisfies the predicate. So hence it must be dropped. So we do not mention x here in the recursive call. But if this predicate breaks at some point, we must return the input list. Exactly, right? So this is just input list. But to return input list, we need access to its tail. But fold does not take tail. It takes an element of list and the result of recursive call. It doesn't mention tail anywhere. All right, so this is how fold works, right? So we have, it takes the combining function, this screw symbol, gets something from a current element of the list and takes the rest of the computation. But it cannot have this value with just consists everywhere, right? So let's, since we started to talk about tails, let's try to implement this tail function using fold right. So in Haskell, actually, this function just returns an exception, right? But for the sake of simplicity, we will say, okay, if tail of the empty list is empty. Let's just, it's our agreement, okay? It's not a recursive function, by the way, right? But how do we implement it using fold right? This is actually an interesting, like technical detail, but I just like those details, these kind of tricks. So implementation of this tail function uses the same trick that Clini used to build the predecessor functions for church numerals. So if you're familiar with church numerals, you will recognize this trick. But how do we go about building this tail function? The trick here is that when you design your function, you have some intended result in your head, right? It should return something. But let's say that this function should return not only this result, but only its input. So you have function working on some list excess. Let's return this excess and the result as a pair, right? So if your language has pairs, which every language should have, you're fine. This can be implemented. So this tail function, this part before second, will be returning the initial input and the tail, okay, the tail of the list. So how does this work? The tail of the this is our input. The tail of input of empty list is empty, as we just agreed. Now, what do we do to keep this invariant, right? So we should invoke our functions, and every time we should keep the input list in the output, and then we should do something meaningful also, right? How do we do that? So folder gets two arguments. This is the current element of the list that we are processing, and this is we start with this empty pair, with pair of empty lists, right? So this is our current tail, basically, and this is our accumulator, which basically tail, right? Because this is our like context. We keep this input list in here. So how do we return the context, the input list? Okay, we have head, we have tail, we just const them together, right? It's our first component. Then what is the result of the function? So remember, the first component is basically our input. The second component is what we intended to do. This is where the real work gets done, right? But the tail of this list is just excess. Okay, so how does it work? Let's look at the example. So we have this list of, by the way, yeah, I forgot to mention that for this function to be really tail, you should just forget about this input, right? Okay. So let's take a list consisting of 3 elements, and let's start processing it from the end. So first it gets empty list, right? New, the constructor. It produces the pair of empty lists. Then it gets element x3. What does it do? it returns the input list, which is x3, and its tail, right, which is empty list again. Then we get the element x2. So we must return the list we have seen so far. It will be x2, x3, right? This is the whole list we have processed at the, until this point. And its tail is just x3, right? And so on and so forth until we accumulated the whole input list and then returned the tail of the list. So this is what this function does, right? The combining function. But that means, so if we can actually like recover this tail, that means we can implement drop while in terms of fold right. We use the same trick. We accumulate this input list, right? And then we do exactly the same thing that drop while does, right? So if the current element satisfies the predicate P, we just forget about X, forget about this element, and return the result. So rec, it's the result of recursive call. But you see, now we have a pair. We have the tail of the list. So we now can use it to leave the list alone, right? If we don't find anything that satisfies this predicate, we don't have to drop anything, and so we just return the initial list. But let's compare the implementations. Which one do you like best? This where folder F or the recursive one? What's your call? What is more readable? Yeah. So yeah, I like this second one also more. Okay. This means that it's not a silver bullet. You should know how to use it, right? But it doesn't mean that you should use it like everywhere. Right? Okay, let me probably skip this part because it's kind of technical. But so instead of using folder, you can implement lots of stuff using folder rec, which is the same as folder, but the combining function also gets the tail of the list along with this head of the list, right? So that's why it gets 3 parameters. And using fold rec, it's really easy to implement drop while, right? Because now we get all the 3 components that we need to build this function. So no more pairs of empty lists. And of course, fold rec is basically it's a special case of folder in a sense. But on the other hand, you can implement fold rec in terms of folder. So this means that folder has the same expressive power as fold rec. All right, so let's get to this fold left example. This is a very cool example. I prefer to do it like in 2 ways. So fold left in a strict language is basically it can be better than fold right because it's a tail recursive function, right? Because you see we do not defer this computation, which can basically recurse again into fold left, right? Again and again. And what it does, as opposed to fold right, it folds the list from the left. So it starts with some accumulator, then it adds this x1 element, x2, x3, and so on and so forth until it goes until the end of the list. So our goal here is to implement this foldable function in terms of fold right. So fold left in terms of fold right. Because like the paper is called on the universality and expressiveness of fold function, right? By fold means fold right. So we should be, in principle, able to implement like almost everything using fold, right? At least the most the classical functional programming functions. Right. So if you rotate this equation along this vertical axis, as the symbol suggests, you will get this kind of expression which resembles what we get when we use fold right, right? Because it associates, the parentheses are associated to the right. But also you see we need to flip the direction here. So that's why I used this weird looking screw symbol, okay? But so we have this form it should be possible to implement using fold right, and indeed it's true, right? But of course, you see that we start from x1, not from xn. So before using fold right, we hit our list, the input list, with the reverse function. And this will get us this kind of expression, right? And so flip of this screw is this one, right? Okay. So this is how we would write it in Haskell, right? For example. Basically the same thing, but without Unicode or LaTeX. All right, so, but the paper actually gives another definition of this function, which is slightly more involved. But when I was sort of inferring the definition of the function, I used this as a source of inspiration. So this reverse is kind of inherent into this, to this problem. Okay, so again, we start with fold left, but now, instead of rotating it, we rewrite it into this equivalent form. So we start, instead of using this application, we use functional composition. Why? Because functional composition, you read it from right to left, in reverse, right? So this was my intuition when I was building this solution. By the way, I suggest you, urge you to read the paper. It has different explanations, so I wasn't trying to calculate here. I'm trying to provide some kind of intuition behind this. All right, so this means that we start with this value v. We hit it with x1, then x2, then combine it with x3, and so on and so forth, until we combine it with xn. This is exactly what this expression says, right? But now we managed to put these x1, x2, x3, and so forth in reverse, right? But it's actually not enough to build this fold right, to derive this fold right. We need some, because these elements, the intuition here is that we're going to be processing the const constructors using this, but we also need to process the nil constructor, right? And for nil, we add this ID, identity function, which doesn't change anything here, right? But you will see it's much nicer. So functional composition is associative. You can put parentheses if you have three functions, right? Composed, f, g, h, you can put parentheses anywhere, right? So why not then put them to the left, as shown here? And again, if you squint hard enough at this picture, you will see that this is basically rotated fold right. Because if you rotate it again, using this vertical axis, you will see that we start with empty list, we replace it with ID, then we do something with the last element and the penultimate element, and so on and so forth, until we go to the x1. So we are basically processing the list from right, from the right-hand side, right? From right to left. And we can rewrite this representation into this form, right? So we start, this is for when the access, the input list is empty, we just basically say ID, and we ignore this thing, right? So ID of v is v. This is what fold left does for the empty list, right? And we basically say, okay, so we have xn, the last element. We say, all right, and hit this thing. So we differ in computations. We're accumulating, and it should be clear that why we need to build this basically closure, right? Because fold right works from right to left, right? But fold left works from left to right. So you basically need to kind of build this deferred computation, and then once you build it, you went through all the list, and you hit it with this initial value, then it like a domino effect, right? It unfold everything that you packed inside. All right, and now Jesus will continue with this category theory stuff.
Bueno.
Okay, so
So it was laser, continue, and okay, yeah, thank you. All right, so sorry, it's because I need to remember that I have the microphone here. Yeah. Okay. Yeah, this is weird. So we are now going to delve into this proof properties of fold.
This one.
Okay. Okay. So previously it was mentioned that if you build your programs using fold, Anton mentioned it around the advantages, the list he provided. So he mentioned that if you build your programs using fold, it makes it easier to prove properties about the programs. Why is this? Why is this the case? It's because fold has a property called the universal property that on the outset what it is saying is that fold is the only function that satisfies those equations. Yes, but there is another, a more intuitive explanation to this. Imagine you have a Lesser, yeah. Oh, okay. Imagine you have a function on lists, such as you define it using pattern matching and recursion and has this form. Then the theorem is telling you that this function can be rewritten using fold. Yeah, when you read it like that, it seems trivial, right? Because that is precisely what we have been doing during the entire talk. It's like we presented you with lots of examples at the start, and we asked you, what is the pattern here? Yes, and so we showed you that all these functions are following the fold pattern. So when I say it like that, it seems that this theorem is just useless, right? It's like yeah, what is the point if you can always rewrite the functions that has this form if I write it into fold? It's just the same a triviality, it seems. So, but it turns out that no, it actually is very useful. Let me show you. Let's suppose you want to prove something like this equation, saying that the sum function that takes some list and adds all the elements in it, and then at the end it adds 1. Yeah? And so this is saying that this composition of these two functions can be rewritten as a fold. Yes. Okay, so on the outset, just by looking at it, it's like, okay, so I have a composition between two functions, but this function doesn't seem that it is defined using pattern matching because it is a composition, right? So how do I prove this? Yeah, well, the usual strategy you would follow here is just do the proof by induction on lists, because these are functions and defined on induction, on lists. But if we use the universal property, we just need to prove this. I am writing the universal property on the right-hand side just for reference. Yes, and so the only thing I need to prove is this. This is G. This is G in the pattern. Yeah, and I just rewrite it here, and then the rest of the equation. This is B. I put it in here. This is we put it again in G. And then this, then F is this. I put it in here. I'm just following the pattern. Yeah. Okay. And then when you simplify these things just by definition, you get this. And this follows just for simple algebraic manipulation. These equations are true for. I won't do the proof, but it's just it's just simple algebraic. This assume of empty list is 0, and then plus 1 is 1. Yeah. So so the point what I want to make here is when you use the universal property of fold, you escape the need to use induction. Yes. You just like go over the hoops, and you just reduce your proof to some algebraic manipulation or some properties of the programs you have. If you already proved another properties of your programs. Yes. Okay. So where does this name for this property comes from? This the universal property for fold. Why it is called like that? Well, it turns out that it comes from category theory. In category theory, a universal object is an object that kind of relates to the other objects in your domain of the... Yes, I am being very vague here, but kind of relates to all other objects in your domain of discourse in a unique way. Another way of looking at the universal object is something like saying, is the object that is the most efficient way of solving a problem. And let's see at the universal property of fold. It's saying fold is the only function that satisfies these equations. Yeah. So it is a kind of an optimization problem in a kind of way. It's like, what is the only thing that satisfies this thing? So it is a kind of universal. That is how in category theory it is. That is how they refer to be something to be universal. Yeah. But category theory is a theory about composition, structures, and relationships between objects. So it makes sense that category theory can formalize this idea of universality somehow, because universality is talking about the relationships between other objects in your domain of discourse. Yeah. And functional programming is also about composition. That is the spirit of functional programming. So it is not surprising that things that you find in functional programming will also have a counterpart in the category theory. And that is the case for fold. And let me show you. Yeah, this will like... I was waiting to change the slide because... Yes. Okay. So, let's start decoding this. It looks like a monster, but it is actually quite illustrative once you see what is going on here. Okay. So category theory has this notion of objects and arrows. They do not. Category theory does not assume any kind of a structure on those things, on those objects and arrows. But for concreteness, I will assume that my objects and my arrows are types and functions, so that I am working in Haskell types, let's say, to make the explanation easier. But my argument will be the same. It doesn't matter. My argument is just a structural argument. That is category theory is all about. It's about a structural argument. So it doesn't matter. Okay. So what is a list object when we are talking about types? A list object is just the type of lists. Yeah. So LA is the type of lists. And how do you characterize this object, this type of lists? Well, this type has two functions. The nil function that picks the empty list. Oh, by the way, this type is the trivial type or the unit type. In Haskell, I think it is written with the parentheses. Yeah. Okay. So, but in category theory, it's called a terminal object. Yeah. Okay. So we have a function that is picking the empty list, and we have a function that is picking the cons. If you read this as a product as pairs, yes, these are pairs of things. You get an element from type A and a list, and so cons will build you the list that has those two things together, yeah, the constructor of the list. So the universal property for a list object, which in this case is the list type, will say the following: if you give me another type and two functions having these types, in other words, this is telling me B is an element in this type, and this is the accumulator function in the fold. Do you remember that it receives the current element and the result of the computation and then combines them into something? Yeah. So the universal property is telling me that if you have this and this, there will exist something, some function between the list type and this type B. Yeah. This name, this thing is just a name. It is not. I am not saying here that I built fold somehow before. No, it's just a name. It's a name parameterized over these two parameters that I am giving here. Yes, it's just a name. Yeah. Okay. So there exists some function that I am naming like this, satisfying the following. It makes the following two diagrams commute. What does that mean? In category theory, when you say that the diagram commutes, it means that any two forking paths in the diagram, any two forking paths will lead to the same result. And following a path means composing the functions along the way. Yeah. So if you read this diagram, it means if you compose nil, if you go through nil followed by fold, it will be equal to V. Yes. So this is what this equation is saying. Yeah. If you compose nil followed by fold, it is equal to B. Remember that composition is always read from right to left. Yeah. Okay. And so this is it is similar. Ignore for the moment this thing. I just want to focus on this part only. Yeah. Okay. So it's saying that if you apply cons followed by fold, I keep forgetting that I have this. Yeah. If you apply cons followed by fold, it will be equal to applying this followed by F. Now, before explaining what these equations are saying, yeah, let me tell you one more thing. I ignore this thing in what I was saying. This bank thing. This is saying that this function that exists is unique. Unique in the sense that any other function that makes these two diagrams commute will be equal to fold. Does it ring a bell? What I was telling you before about the universal property of fold. Fold is the only function that satisfies certain equations. Let's look at these equations. Yeah. What are these equations saying? If you apply fold on nil, is equal to the value you return in the base case. Do you remember that? How do you define fold? Yes? Okay, so, and now let's decode this one. This is saying this function with this symbol is just a way of saying that if you have a pair in here, you will apply this function to the first component and this function to the second component. Yes? Okay, so I am write it here in a point-wise manner to make it clear what it is doing. Yeah, so if you apply fold on cons on a pair in here, an X and a list, yeah, it will be equal to F of this function applied on this pair. But what is this? This just applies the identity function on X and fold on L. And so you get this pair. So it is F applied on this pair. Yes. So this is saying this is just the defining equation of fold for the cons case. Do you remember? Just fold on cons is just applying F on X on the result, followed by the result of the recursive call to the rest of the list on fold. Yeah. All right. So these are this is what I was told you. This universal property of a list object is just the universal property of the fold. It's just the theorem I showed you before. Yes. But now, where does this come from? Because this is just a definition. It's just, yes, it is a list object. Where do you get these things from? Yeah. So it turns out that you get this thing from what they call an initial algebra. Yes. What is an initial algebra? I was going to swear. So it is an initial algebra of the list functor. Yeah. Well, what is this doing? You can imagine a functor as a way of constructing iteratively, starting from the empty type, some type. Like, for example, let's say that I start with the empty type with the empty type. And so what will happen if I execute this functor on the empty type? It is saying I will add something, which I will think of this as the nil list, and add to all the previous things that were already built in X, which in this case, since it is the empty type, there is nothing in there. So it will only add the empty list at this step. Now, repeat that step again. Now, you get the type that only has the empty list in here. You give it that input in here. Yeah. So what will happen? It will add the empty list again, followed by it will cons everything you built in the previous step. So you will have now all list of length 1 plus the empty list. Yeah. Do you see that? If you keep repeating this, at some point, you will keep adding in this type, you will keep adding all the list of every length, like, and what this thing is converging to is the type of list or the list object. So an initial algebra is just this converging thing towards the functor is going to converge. Yeah, that is what is an initial algebra. And when you build an initial algebra, which in this case is the list object, you get this function, which acts as the constructors of your list. How? What is the definition of this? Is this, right? So you get 1 plus A times LA. Yes? What is this? But this somehow is encoding the two constructors of the list. If you give me an element of 1, that means that this is picking the empty list. If you give me an element of the other case of A times LA, that means that it is the cons constructor. So this function is packing the two constructors somehow in there. Yes. So until now we have the list object and its constructors. So what is the universal property of an initial algebra? It says that if you give me another type B together with some function that is packing two pieces of data in the same way that this is packing the two constructors of the list, which two pieces of data are this? It is the initial value for the fold and the accumulator function for the fold. Yeah. If you decode this, you will notice that. Yeah. Okay, so it says that if you give me this piece of data, I will give you a function from the list object, or the initial algebra in this case, to type B, which I will call it kata F from katamorphism. It's because fold is just a special kind of katamorphism, and in the general case, we can call them katamorphisms. Yeah. So I will give you this function that makes this diagram commute, and it will be unique. This function will be unique. So this diagram is saying that this equation is true, right? It's just in followed by kata F, and this followed by F. Yeah? But what is this saying? Yeah. So I told you that this function is encoding the constructors. So this is saying if you apply the katamorphism or fold on an element that is in the form of a constructor, imagine a fold on the empty list or cons, yeah? In the form of a constructor, it will be equal to applying the accumulator function or the folding function on this thing. And what is this thing? It is this thing by definition. Yeah, I didn't explain this. What is this thing? It is explained here. It is just the mapping of the functor, the mapping function for the functor. And what it does is that it takes a function and leaves intact the empty list, and conses are leaves intact the element in the first element of the pair, but applies F on the second. So what this is doing is it will apply kata F on the sublist and leave everything else intact. Yeah. So map is encoding the idea of applying recursively this function on the subcomponents, followed by the folding function. Will give you the equations of what fold is in general. Yes. So why am I telling you all this? It's like this is too complex, too abstract. Let's say, okay, yeah, if you change the functor, you will get using the same construction and the same equations will tell you what should be the fold for your new data type. Yeah. You just need to change the functor. I am here using the functor for the one that builds lists. Yeah. But this is too abstract. Why am I telling you this? Well, there is an easier way to know what should be the fold for some data type. I will go through that after this. But I just wanted to show you that there is a framework that allows you to reason about any data type you can come up with. And you can prove things about any data type using this kind of language. Yeah. It's just a framework of reasoning. Yeah. Okay, so how do you get the fold that that does not involve all this crazy stuff, unreadable stuff? Yeah. So how do you do it? Okay, so let's go back to lists for the moment, yeah? And let's see what will happen if I apply fold on cons on the constructors of list. Fold on cons and the empty list. What do you think that the fold should do? By the explanation and told you before, earlier, a fold just replaces every cons for the folding function, right? And the empty list for the initial value you give. So if this is saying that I will replace every cons for cons, and the empty list for the empty list. So what intuitively is this doing? It is doing nothing to the input list. It's like the identity function. Yeah. So if I use the universal property, this is I am using the theorem I showed you in the blue box. Yeah. If I use the universal property, according to universal property, if I want to prove that this is equal to the identity function, I just need to prove this, and this follows trivially. This is just identity on empty list is the empty list, and identity on this is just this. But what is the other side? Identity on XS is XX, and what is cons? Is X cons XS. So these are trivially satisfied. So this is true, according to the universal property of fold. So it seems as if a fold should satisfy the following property. When you apply fold on the constructors of your data type, it should behave like the identity function. Yes? It seems that there is one property, and indeed it is, and it applies to any data type. You can prove it using category theory. Using the diagram before I showed you, you can show that that property indeed will hold. Yeah. So that is the first condition that a fold must have, or a catamorphism must have. If you applied the catamorphism to the constructors of your data type, it should behave like the identity function. Yes? Okay, that is the first condition. Second condition. Let's look at the implementation of fold for lists. It needs to pattern match on the constructors of your data type. Third condition. It needs to recurse over the subcomponents of your data type, which in this case is just the sublist. And the last condition is it needs to combine the results of those invocations, yes, somehow, using some folding function or whatever. Yeah, it needs to do those things, and it needs to map the initial values somehow. So let's keep in mind these four conditions. It should behave like identity on constructors. Should pattern match. Should recurse on subcomponents, and should combine. Yeah? So let's suppose we have these two data types. These trees, leaf trees, are just trees where there is only data on the last level of the tree, on the leaves, and the nodes do not have data. They just splitting, like building the structure of the tree. But binary trees are the ones you already know. It's like every node has a piece of data on them, and yeah. Okay, so how do we build the catamorphism for this, or the fold for these data structures? Well, the catamorphism will need to build some function out of your data type into some arbitrary type B. Yes, that is what a catamorphism does. It's okay. So, but what should be the parameters in here? So the strategy you need to follow in this case is first list the constructors of your data type. For example, let's focus on the leaf tree, which has these two constructors. Yeah. So what is the type of these constructors? It says, well, you can see them here. Okay. So how do you add these parameters to your catamorphism for leaf tree? You just replace every occurrence of your data type in the constructor for the target type. So this becomes BBB. This is the first parameter. Yeah. And then go to the second constructor. There is an occurrence here, so replace it with B. So this AB becomes your second parameter. Yes. The same happens with the other data type. ABBB, ABBB, and B. Yes. Okay. So until here, this is just building the type of your fold for this data type, or the type of your catamorphism. Yeah. So what is next? Now here is where we need to use our properties I was listing. Second property said that you need to pattern match. These are pattern matching. Yeah? Okay, we have that. Simple. Yeah. Third property said that you need to recurse on the subcomponents of your object. In this case, the subcomponents of this tree are the left tree and the right tree, so you need to recurse on those subcomponents. Yes? Easy. Fourth condition, you need to combine those things. So you need this, put this into the function, you receive the subparameter. Yes? This one is determined. There is not much you can do with it. It's like you have an x of type A, so you just apply FL on x and you get B. There is not much to do here. But I've not said anything about my first condition. Do you remember the first condition? The one that said that your false should behave like the identity type when applied on the constructors of your data type. So what happens if I switch these two things in here? If I say no, I will say I will recurse the result of the recursion of the right tree. I will insert it here and then put this in here. What do you think will happen? Let's say you have a tree that has the form of a leaf tree that has the form of has a 3 here on this branch and a 2 on this branch. When you you need to imagine it. Sorry. When you give this tree as an input to this function and the flipped one, it will reflect the tree. Oh. It will reflect the tree. So it is not behaving like the identity like the identity function. So that condition is important. So it means that if you flip these two things, it is not the catamorphism you are looking for. Yeah. You need to respect that property. All right? And so this is just following the same strategy. It's just for binary trees. Okay, so now we will continue to the last slides, and then we move to the interactive session with Kok. Yeah.
By the way, do we can you hear me? So do we still have time for the last part? Okay, fine, great. So this hardcore category theory stuff, I guess it's over, right? And we go, at last. So, right. Why do we care about proofs of properties? So, for example, Haskell compiler has this pragma thing, like rules. So you basically can say, all right, like, dear compiler, for the sake of optimization, replace these things with this. So, for example, if you have, let's say, 2 maps over a list, right? It doesn't really make sense to traverse the list twice in memory. It makes sense to traverse it once, but hit it with the compositional functions, right? It's like trivial optimization. And a good compiler should do that, right? So in some languages, like in Haskell, it's governed with these rewrite rules. But you see, the thing is, the compiler trusts you blindly. So whatever you write here, it's like it's up to you. These rules must be sound. So if you write something here that is not really true, doesn't really make sense, then yeah, you just screwed up your compilation process, right? You will get something that might not be a legitimate implementation. So we need to make sure that this is just a very simple equation taken from the Haskell source code, but you can imagine that it can get hairy, right? You can have lots of deep nesting, lots of equations interacting in some weird ways. So to ensure that everything is correct, we can use and let's say some formal methods, some tools, and there is a company, App. They have this their guy in here, and so they are writing a library for Scala, which involves some complex stuff with optics, lenses, and so on and so forth. And so they want to make sure that this library is actually correct. So they use not only pen and paper proofs, but also employ interactive proof assistant called Coq to make sure that this is true. So let me switch to Emacs, right? So this tool that I use primarily these days, this is the thing I actually use at work every day. So this is an interactive proof assistant. Let me actually skip a bit this preliminary part because I just wanted, since everything in here is Haskell or resembles Haskell, I wanted to make sure that what I'm showing you here will resemble Haskell as well. But Coq does not adhere to that style really, but it lets you imitate it. So this first preamble is basically me imitating Haskell in Coq. Okay, Coq is C-O-Q, like this one, right? Okay, so let's see how you work with this thing. When I'm pressing like Control C-N, I'm saying, okay, let's check a little bit more. So basically, Coq is a type checker, and this is, if you think about it, this is really amazing. So before, when you did your proofs, let's say in high school for your geometry class, or your calculus class when you were an undergraduate, right? You had this assignment, like prove that this theorem or lemma is true, right? You go home, you sit, you think hard, you like, okay, here's my proof, but is it really a proof? How can you tell? Yeah, you need a person, your tutor, your teacher, right, your professor, who would say, yeah, this is a proof, like this is correct, right? You needed a person to actually do this checking for you when you're just at the beginning of your mathematical journey, right? But this piece of technology, it allows you to just forget about that. You have your computer who will check your proofs for you. And how does it work? There's this thing called Curry-Howard isomorphism. It's a huge topic, probably worth another talk. I'm not going to go into details, but it basically allows you to reduce this proof checking to type checking. And type checkers are pretty well understood pieces of technology. Okay, so I'm... Can you hear me? So it turns out that I need a proof assistant, a real human in here, right? Holding the microphone. Okay, so basically, as a programmers, you are used to either basically like running your code in some kind of interpreter, right? If you're working in a dynamic language, or you compile your code and you run it, right, somewhere. But when I do my job, I'm embarrassed to say that I only type check my code. I don't run it. Okay, so what I'm doing here, I'm just type checking piece by piece this code that you see on the screen, right? And so let's skip to some interesting part, because here you can see that basically this is the same code we have observed before. Just keep it, okay? So this is the same code we observed before. We can define this length function. We can compute. You see here. it is 6, right? The length of this list is 6. Okay, we can define this reverse function. We can define map exactly using fold or fold right. We can define filter. It's like trivial, right? But this property that Jesus was talking about, so this universal property, one of its consequences is this fold fusion law. And here we start to deal with proofs, not just functions. So before, what you see on the screen, this length reverse map, these are computable functions. You can actually execute those. And for example, from Coq, you can extract code into different languages. Like you can extract it to OCaml and run it, of course. You can extract it into Haskell, which doesn't work as good as extraction to OCaml at this point. And you can extract it to Scheme, which is a dialect of Lisp, right? So what this lemma says, it says if we have, let's ignore these couple of lines. It says, okay, if we have a fold which composed with some function h, then it can be rewritten as just a fold, provided that you have some conditions imposed on this h function, right? Okay, so a proof that I would write would say something like this, which I guess if you are seeing this Coq proof assistant for the first time in your life, it's like some black magic probably, right? It certainly was for me at some point. But let's go like line by line over this with this manual approach, and maybe you will see what proof assistants are like. This is like the main goal of this part of the talk, to just basically give you this feel, what it feels like to use a proof assistant. Okay, so hello. Okay, hello. Can you hear me? Okay, thank you. Yeah, let's retire this human. We don't need him anymore. All right, so let's see what we're doing. Let's take a look at this part of the screen. We have our goal in here, which is basically an implication. We're saying, all right, if H acts on W like this, so it returns V, and then we have this weird-looking condition on a function H in this form, right? Then this should hold. So we can rewrite our fold function followed by some H into just fold. How do we do that? So how do we do proofs with pen and paper? By the way, can you read this? Okay, that's cool. Yeah. We're saying, all right, so we have some premise. Let's move it into the context. What is a context? A context is just a bunch of things that you already have. So you know that this H of W is V. It's the same thing as you can see in mathematical text. Let's assume that. So the stuff in the context that you have assumed or proved otherwise. All right. So we have assumed that this holds, the first condition. We have assumed that the second condition holds. Now we are left with proving this kind of strange-looking thing. What is equals 1? Well, let's print it, right? You will see the result in here. So this is why it's called interactive, right? Because the tool is interactive. So down below, you see to the right, you see this thing. So this is actually equals 1. It's called a notation, basically syntactic sugar. It stands for ikfun, this thing. And what is ikfun? Well, if you see, if you look here, it's basically saying, all right, so two functions are equal as long as they, for all x's, they return the same values, right? This is one of the definitions of equality on functions. So we will use this one. By the way, about this syntactic sugar, let's unset notations. And you see what it looks really like. Well, not exactly. If you want to see what it really looks, set printing. Oh, okay. So this is exactly what Coq sees, but of course, it doesn't really make sense for the human prover, right? So this is why we hide lots of stuff. And sometimes when things break, you don't know what to do. Just set printing all and go figure out. Yeah. All right. So we just figured out that equals 1 stands for ecfun. Then let's just unfold it. This rewrite slash ecfun just unfolded the definition, right? You see this for all x, these two functions acting on x, they're acting the same, right? And now instead of equals 1, you see just equals. And by the way, in Coq, equals is encoded as a data type. It's not a primitive. But yeah, let's not go there. So when we say that for all lists we have this equality, okay, assume we have some kind of list, right? We move it to the context. Okay, so now we see something a little bit more comprehensible. Okay, how do we prove these kind of properties? We use induction. And this elim basically means let's do induction on the structure of the list XS. All right? So when we do induction, list has two constructors, the nil one and the const one, right? So we are left with proving two sub-goals. You can see we have two sub-goals up here. All right, so what do we do next? Let's unfold what it means to compose functions. And I just happen to know, because I just wrote this notation up there, that this circle, the Unicode symbol for circle, stands for comp. So we unfold it, and of course, composition of functions unfolds to just functional application, right? We apply one function, then we apply the next one, okay? Now, what do we need? We need to, by the way, what does this fold equal to? This one. Fold of G of W of empty list. Universal property? W, yes, W. And here, it's equals to E, right? So if we unfold the definition of fold, we get this one, right? So we basically substitute fold into the equation. So now you can see why we needed this equation, H W equals V, because H, V, and W are arbitrary things. You cannot look inside them. They're like opaque, non-transparent at all. So if we did not put this equation into premise, we wouldn't have any means to prove this sub-goal, right? So when actually I started to prove this lemma, I did not put the premises in there, and I just sort of inferred them. So whenever I got stuck, I just, okay, I need to add this one. That's all. This is how you do this thing. Or you could just read the paper, and it actually lists those premises, all right? So now we rewrite the equation we got, and now we see that there is this trivial equality, and it can be resolved using this. By the way, these things are called tactics. And I'm using this assets reflect proof language in here, which is not really super standard in Coq. So yeah, reflexivity, if you have seen Coq code, you would recognize rewrite reflexivity, but probably elim would be newer and move. Okay, so reflexivity says, okay, you have trivial equality, x equals x, 42 equals 42. I know how to deal with that, right? So at this point, we have finished with this sub-goal. So we just proved the first part when we were dealing with empty list. Now we're dealing with the inductive step, right? So we have head of the list, tail of the list, and we have our induction hypothesis, as always in proofs by induction, right? So let's assume we have those. So you can see that we have this induction hypothesis. It's basically the solution, like the proof, for the smaller problem, right, as always. But we need to prove it for bigger lists, right, for the one that has X. And also, in Coq, it's customary to say of type just colon, and double colon means const. So like exact opposite as in Haskell. All right, so let's try to sort of rewrite with our induction hypothesis. But as you can see, Coq tells us that the command indeed failed, and if I didn't put this thing, so I'm saying, okay, I'm expecting that this will fail. I know, right? Otherwise, it will give me some error. This is where it guides you, right? So if you do something stupid, it says, no, you cannot do that. It's not allowed, basically. Okay, so let's try to simplify stuff. And up here, what I was doing, I was actually simplifying by hand. But Coq can do it on its own, right? It knows the definition of functions. And there is a tactic, or tactical. This one, it says, okay, let's simplify. Okay, we simplified a bit, and we get something over here that looks like the right-hand side of the induction hypothesis, right? So that means we can rewrite using it. But we have to rewrite from right to left. This is why we have to put this minus sign here. Okay. We can now simplify it a little bit more, again, using the same tactic. And we have our equation E2. So at this point, if we had not added this equation, we would get stuck. So this is how you infer what should be added, right? Okay, I rewrite. You can see that the right-hand side and the left-hand side are exactly the same. So reflexivity can again deal with this kind of situation. And this kind of field square stands for QED. Here I'm using one of the plugins that prettifies symbols for me. So this is actually ASCII QED dot, but it renders it with this square. Okay, what does QED do? It does type checking. It type checked whatever you built using these tactics, and you build this thing called proof term. So I was basically writing a functional program in here. So this is part of Curry-Howard correspondence. And this QED, when I hit it, sorry, I already did that, right? It actually checks that the body of the function I was building corresponds to this type I gave. So equality is a type in Coq. All right, so let me demonstrate you just, I was going through all these details, right? So how we rewrite this and that, but the proof can be automated. You can have tactics that are kind of intelligent. So for example, here we are saying elim. It's basically induction, do induction. And then we say, okay, simplify, and then we say congruence. Congruence is basically tactic which can solve your goal if it can be solved with some sequence of rewrites. So it does all the rewrites, and then it says maybe you have some impossible situation, like you have some non-empty list equals to empty list in your context. Like assume we have this kind of equation. It will deal with that as well. Okay, so this example of sum fusion, right, which was given by Jesus, we can prove it by induction, as I did here, but it's much easier to just apply our lemma. I'm saying apply a fold fusion, that's all. So we have this, again, sort of universal property, like a special case of universal property. And I'm saying, okay, apply this thing in this case. And Coq is smart enough to figure out all these functions. So it sees, okay, +1 stands for h, and so on and so forth. So it figures it out by unification. And it says, okay, yeah, you already proved a more general result, so I can just reuse it. That's all. So this is where it gets really, really useful. Or let's say we have map fusion, that example that I mentioned before. So if you have two maps, it makes sense to just map it once, because it will result in one traversal of the list, right? It's more efficient, usually. Okay, so this is maps. We have implemented those as folds, and that means that it's just the same instance of this more general law, fold fusion, that's all. So this is how you can check your equations. You basically prove it. Okay, let me skip this recursors versus iterator stuff because we didn't have time to cover it. Okay, for example, let's take a quick look at this thing. So fold left, here it's recursive definition, the same as we have seen before, right? We can implement it using fold, this rec, then we have to hit it with this flip function, right? Or we can implement it using this reverse approach, right? But when I was presenting that material, that example, I was like giving intuition, right? It wasn't really a proof. Now we can actually prove that these three approaches, they give us the same function. Well, the same, not in case that they behave in a totally like exact way, in the exact same way. The same, that means that they will act on inputs in the same manner, right? The same result. But for example, one of them can be more efficient than another. So these time considerations, we do not care for them at this point in this setting. So this is basically saying, yes, these three are equivalent because we can prove these kind of lemmas for them. So fold L rec is equivalent for fold L using reverse. Okay, others? Yeah. Okay, maybe I can use the okay, well, almost done. So yeah, as you can see, we can prove a couple of lemmas which are stating that fold L using recursion is equivalent to fold L using the reverse function, or fold L using fold right, that approach. And so in this case, when I'm proving stuff, we cannot say like this is correct. No, it's not even right. You can say that something is correct with respect to its specification. So what is specification in this case? Well, my specification is exactly this fold left function using recursion, because it's really clear. It's much more clear than any other implementation, like this one or this one, right? Do you agree with me? You can read this one and say, yes, I believe this is correct. Fold left returns v on the empty list, and it just basically recurses, does this tail recursion thing on the rest of the list, right? So this is like obviously correct. This is our specification. So functional programs, if they're sufficiently simple, can serve as specifications, right? Okay, but when I look at this function, I might not believe that this is fold left. It's not obvious, at least to me. Okay, and the same here. It's not obvious that this is the correct implementation of fold left, but we can use this kind of technology to actually prove that. So this one says, okay, fold ref is correct with respect to this function. So it's like golden standard, right? It's like reference implementation, IK specification in our case. All right, so at this point, I think we should wrap up. So this file has some more stuff, as well as the... Oops, sorry, where is the slides? Yeah. Thank you. Feel free to get in touch with us anytime. The slides are available here on my GitHub. You can see like more stuff in there. You can go through this Coq file, ask questions, whatever. Thank you very much for coming. Do we still have time for questions? If there are. Okay, yeah. Yeah, fire away, feel free. Anything.
So when you talk about initial algebras, but then you showed the example with the trees. Is it exactly the same? Is it an initial algebra, or you're using a generalized algebraic data type, and you can use the same analogy to define a fold for any combination of plus and times?
Yes.
It doesn't need to be, and it can be an arbitrary thing.
It can be well, yeah, of course there are conditions on on what kind of functors you could use. Usually data types are usually what they call a polynomial functor, usually fit into that kind of pattern. And so it depends on properties of the category in which you're working, if that functor in particular will have an initial algebra or not. But for example, if you work in the category of types and in the category of sets, you know that any polynomial functor there will have an initial algebra. So of course, that is usually the categories in which we work in. It's like, we tend to think of types as some kind of set or.
The initial is that it has a 1. Or what does it mean to be initial exactly? What can be generalized?
Oh yes, If I give you an arbitrary functor, just forget about this definition. This is just the particular functor I am using here for building the lists. But suppose that I give you an arbitrary functor. I don't give you the definition of it. It's just a functor. Yeah. So an initial algebra for that functor will be an object together with an arrow going from the functor applied the functor applied on that object into that object. That will be such as the following universal property holds. Like for any other algebra on that functor, there will be an algebra morphism. This kind of thing is called an algebra morphism, but I didn't mention that. Yeah, but that is the universal property. It is in general. Any functor, as long as it has an initial algebra, if it has one, it will have this universal property. And usually, data types, the usual data types we use, are usually fall into this polynomial functor kind of pattern. So yeah, they usually have initial algebras, and especially in sets and types, yes, they do. So for example, if you want to use the let's say the leaf trees. What is the functor for leaf trees? In this case, since it has a constructor with that builds a leaf, right? Let me. Sorry. This one. It has a constructor that builds a leaf using some element in A. So one of the branches in the functor will be, instead of 1, will be A here. Yeah, and then the other one. The other functor will be it splits into two things. So this is the recursive part, and to build the functor, you just need to replace the recursive part of the other type for the input to the functor. So it will be x times x, the other one. So it will be A plus x times x, and that will give you the initial algebra corresponding to leaf trees.
Okay, thank you.
Any more questions? Very nice talk, first of all. I guess there is a property for unfold, for the anamorphism, a universal property. Is it so useful? Is it as useful as this one? And what about the support in Coq for coinductive types?
For anamorphism, it's a little bit different, right? Because basically you have to stop, right, at some point. Yeah, but this is not really a definition of coinductive type, right? You will have some trouble trying to working with that. You will have even trouble trying to define it, like for example, like fixed point, right? The thing is, the Coq functions, they have to be total, and to be total, that means you have to recurse on smaller subcomponents each time. But for anamorphism, it's not the case, right? You cannot do that. But
There
yeah,
was another type of recursion. It's not structured recursion. It's
yeah. There is data and co-data, right? Data is what you destruct, and co-data is what you produce, you construct, right? They are kind of dual, right? So yes, and actually, when you try to work with this in, let's say, in Haskell, it's much easier, right? Because you don't have those restrictions on this, and you can produce very nice algorithms using compositions of katamorphisms, anamorphisms, paramorphisms, hilomorphisms. Basically, if you fix the structure of your algorithm, so if you like pick, I want to, let's say we're talking about sorting algorithms. I want to implement some sorting algorithm using katamorphism, and it will get you insertion sort, basically. So when you fix the structure of your algorithm, this is why these recursion schemes are really cool, is that you can basically infer different types of, let's say, sorting algorithms. Did I answer the question?
Yes,
okay.
thank you.
Thank you.
Any more questions?
There's one part in the paper when the author is dealing with the fusion rules, in which there is a part that appears in an equation in both sides. So he relabels that part with a y, like a new variable, and now he can say these functions are the same. So if it feels like you have to make an identification, like it's something that you have to really look at it and say, okay, these are the same. I can relabel this part in both sides by a new variable, and that variable is free and it's not constrained in any way, because it's really f of x, and I guess that x is free and f of x is as free as x was, although of a different type. My question is about how does Coq deal with does it do this replacement, or it doesn't really deal with it? And I'm not sure if I'm transmitting this part of this relabel is valid, because if f of x is free, then if x is free, f of x is also free, or as arbitrary as I want it to be. So I can relabel it with another variable, and then that variable I can say for all y, as I did with for all x. Do I?
Well, you cannot really work with free variables, right? I mean, they are convenient in some contexts, and especially in papers when you can infer basically what they mean, right? It's like either for all or exists. That depends on author. So in Coq, you can see that these variables, alpha, beta, and gamma, those are type variables here. They stand for types, and f, v, and etc. Those are basically for all. So when I write it like this, I can rewrite it into an equivalent form. Let me show you quickly. I can do it this way. So this is what these sort of free variables stand for. So they're not really free. They're bounded by for all in here. So this is what we would get, and here I will have to move more stuff into my context, right? So I will have to say something like this. So since this is for all, we can say, okay, let's assume we have some type alpha, some type gamma, some beta, some type gamma, some function f, v, g, etc., etc. So we can assume all these. This is because these are bounded by for all. Did I answer the question?
Not quite, but maybe we can talk about it later.
Okay, okay. Oh, okay.
When one does an informal proof in paper,
yeah.
one introduces this free variable. So it is kind of, I don't
the kind of generalization, right?
Yes,
You can see it in the paper if you have it there.
Yeah.
I think you had it, and it's.
It is kind of,
If you go to the fusion room.
variable will be implicitly universally quantified using the proof. It's like introducing a claim somehow. Right?
Yeah, I mean, two functions are the same if for every x, f of x equals gx.
But
And if I have f of h of x, I can substitute it by f of y. Like h of x is just some convoluted way of another variable that can range over all the values.
I would say that the author uses these free variables in just an informal way to construct his functions, right? So he wants to infer the function's bodies, and this is like I don't know, some kind of informal step. It's like principled approach, but still kind of informal.
And in Coq it will be done differently.
In Coq I would just have to write the function, right?
Okay.
I cannot really infer, right? So Coq cannot express this kind of inference algorithm for function bodies.
Yeah.
Okay.
You have to like provide, okay, here's this function, but
Okay.
how you constructed it, it's up to you.
Yeah, it's because you work with proofs. So
Yeah.
that kind of argument is actually not a proof. It's a proof only when you know already the construction and you read it like kind of backwards, right? It's like this kind of informal things. It's like they are guiding you towards what should be the function. It's weird.
But it's a good question though, thank you.
Thank you.
Any more questions? Okay, so we can wrap it up. Thanks again.
Thank you.